Let's start to talk now about capacitors with dielectrics, and let's think about how they work and how they affect the system. So a dielectric is an insulating material placed between the plates of a capacitor. If you wanted to imagine what this might look like, you could imagine your capacitor as maybe two thin sheets of foil, and your dielectric would be a thin sheet of something like plastic in between the sheets of foil. So a dielectric, that piece of plastic in between the plates, it kind of has three functions. It keeps the metal plates from touching each other. That's very important in a circuit because if the two plates touch, they'll short circuit. It increases the maximum possible potential between the plates, and that's an experimentally observed results. And it also increases the capacitance compared to a capacitor plate if it only has air between the plates. So let's start to set up our situation. Let's say that we have a capacitor and we connect the capacitor to a battery. A battery or a source of potential. Let's say that our battery has potential delta V 0. Okay, so that's where we start. We know that once we connect the capacitor to the battery is going to charge up the capacitor. One plate is going to be positively charged, one plate is going to be negatively charged, and then the result of the separated charged plates is going to be an electric field between the plates. I don't draw in 3D super well, but I'll do my best here and hopefully you can kind of see what's going on. So these arrows represent the electric field between the plates. When our capacitor is all charged up, let's write down what we know about what's going on. So it's all charged up. The net charge on each plate we're going to call Q naught or Q0. Of course, we'll have one plate positive and one plate negative. The potential on the plate we said was going to be the same as the battery. So this is when the plates are fully charged. And we know the relationship between charge and potential that gives us capacitance. So the capacitance of this capacitor in air or a vacuum is C naught equals Q naught over delta V naught. So this is everything we've already done so far. We've just put zeros on it to indicate we're in a vacuum or in air. The charge density on each plate is sigma. We'll call that sigma naught is charge over area. So when we write down that our capacitor is equal to epsilon naught A over D, we use epsilon naught for the permittivity of free space because we're in a vacuum or in air. Okay, so this is the familiar stuff we've already done. Our capacitance is C naught, charge is Q naught, potential is V naught, and charge density is sigma naught. Okay, the next thing we're going to do is we're going to take our capacitor, which has been connected to a battery so that it can get all charged up, then we're going to take away the battery. So we're going to remove the leads. After we take away the battery, we're going to put a dielectric between the plates. What happens when you take the battery away is there's no more connected circuit. The charge can't flow anymore. So that's a pretty important result. Charge can't flow. Because the battery is gone, there's no more circuit. If the charge can't flow, that means that the net amount of charge on the plates can't change. So that's kind of our foundation for this whole discussion, is that the charge on that plate cannot change. Okay, let's keep going. Let's write down the result of what happens after we take away the battery and we put in this dielectric. So let's write down the conclusions of what happens. First thing that happens is that the charge is the same. Okay, so charge is the same. If you wanted to give it a new symbol for charge, you would say that Q is equal to Q naught. I suppose you might use plus and minus because one plate is positive and one is negative. Okay, if the charge is the same, and we haven't cut apart our plates or anything, the area is the same, so the charge density is the same. Because charge density is just charge over area. So our new charge density is equal to our old charge density, and of course it can be positive or negative. Okay, next, we definitely see, if we hook up a voltmeter to our capacitor, we see that the potential between the plates changes. Okay, so our new, and that's an experimentally observed result. So the new potential of the plate, so the potential changes to what we'll call delta VC. So this is the new potential of the capacitor. And the experimental result we see is that new potential is less than the potential to which it was originally charged. So we'll put in brackets, experiments show that that's true. Okay, let's see if we can put this together a little bit. Let's start and let's write down our definition of capacitance, and let's think about it in terms of what we know about the charge and the potential right now. So, C is our capacitance. It's charge over potential. Our charge is Q naught, because remember, our charge couldn't change because we disconnected the circuit. The potential, after we've got the dielectric in there, is delta VC. Okay, this Q naught, well, we could grab a term from over here. Q naught is C naught times delta V naught. And we're still dividing by our delta VC. This is looking kind of good. Let's just pull our C naught outside and put brackets around our delta V's. Now, delta V naught over delta VC is greater than 1, okay, because we know delta VC is smaller than delta V naught. So this number is greater than 1. Our conclusion is that our new capacitance is bigger than our old capacitance. If we put a dielectric in between the plates, we increase the capacitance of the system of the plates. The reason that's important is, remember, capacitance is related to energy. If we increase the capacitance, we can increase the amount of stored energy. Okay, so that's how it works. I'm a person who always asks why. I really like to know physically what's happening here. So let's think about what's happening with our dielectric and what's happening with the electric field, and how do we get this changed potential, and kind of where does this change in capacitance come from. So our dielectric is made up of a whole bunch of molecules. When we make our plates and we charge them, we make an electric field between the plates. Okay, so that electric field is still there even when we put the dielectric in. So the field that happens right here, it doesn't turn off just because we put a dielectric between the plates. So the black arrows I just drew, that's my original electric field. That's the electric field between the plates due to the two charged plates. But then something neat happens with our dielectric. The molecules in the dielectric, they're in this area with electric field. The molecules have charges, of course, so the molecules start to flip over and they start to line up with the field. So the little molecules will be repelled by that positive plate, and the negative end would be attracted to it. So those molecules start to flip. And that happens throughout the dielectric. Your molecules flip so that the positive end is pushed towards the electric field, the negative end is attracted to the positive plate. If we're getting all these molecules line up, what happens is this end of the dielectric tends to have a net negative. So there's a net negative side of dielectric. And then over here, where all the positives have lined up on this end tends to a net positive side of the dielectric. One side is negative, one side is positive. The thing that happens is you get an electric field created inside the dielectric itself. Okay, so we have two electric fields going on. I'm going to label this one E. Okay, and since this is an induced electric field, I feel like I should give this a different symbol. I'm going to call that E with an I. So the molecules line up and an electric field is induced inside the dielectric. So let's have a look at what happens with that electric field. So let's do an electric field analysis. This slide has definitely gotten too full. Let's move on to a fresh one. So I'm not going to try and draw in 3D because that's just too hard to do. I'll go for 2D. So without my dielectric, if everything is just in air or a vacuum, because air and vacuum aren't very different, I have my two plates. They get all charged up so that I have one positive plate, one negative plate, and I get my original electric field established, where that field is due to the two plates having an equal and opposite charge density. And that's my field, my original electric field, E naught. Okay, that's what I start with. Then what happens is I stick my dielectric in there, and all those molecules start flipping, and I get my new induced field. So now I have two fields that happen. To get my net electric field, all I have to do is a vector addition. So my new total electric field between the plates is the vector sum of the original electric field and the new electric field. So EI. There we go, the induced electric field. I see that my original electric field points to the left, my induced electric field points to the right. I'm just going to put in an x coordinate system that points to the left. Take that to be the positive x direction. So my new net electric field will have a magnitude of my original electric field subtract my induced electric field. So I'm subtracting because those two vectors are in the opposite direction. This will give me the magnitude of my new field. Okay, so we've established that we're going to get a new total electric field, which is a result of a field due to the plates and a field due to what's happening inside the dielectric. We add the two fields and we get the new total field. Let's make a definition. I'm going to define a quantity that I call kappa. So this is the Greek letter kappa. Looks like K, but a little bit curlier. Kappa, I'm going to define as the magnitude of my original electric field divided by the magnitude of my new electric field. Well, my old electric field is bigger than my new electric field because I get the new one by subtracting something. So that should be a comma. So my old field is bigger than my new field. That tells me that my kappa is a quantity that's greater than 1. This kappa is what I call the dielectric constant. What can we say about kappa? Kappa is a quantity that tells us more or less how the molecules inside a dielectric can polarize when you stick them in an external electric field. As you can imagine, that depends on what kind of material you have. Some have molecules that are easily polarized, some not so much. So different materials will have different dielectric constants, and you can certainly look those up. So I think a good question might be, what else can we do with K, or kappa, sorry? Where else can kappa get tied in? I'm going to see what other places we can find it. Well, from kappa equals my original field divided by my new field, that tells me that my new field is my original field divided by kappa. Just a little bit of cross multiplying there. Well, my original electric field, now remember our result from Gauss's law, the electric field between the plates of a capacitor is the charge density divided by epsilon naught. Okay, so the original field between the plates is charge density over epsilon naught. Epsilon naught times K is something that we call epsilon. So this epsilon is called the permittivity of the dielectric. So our original electric field is sigma over epsilon naught. That's our E0. That tells us how electric field can move through a vacuum. Epsilon naught times kappa tells us how an electric field moves through a material. So let's write that part down. Epsilon equals epsilon naught times kappa. That's the permittivity of the dielectric. What else will we talk about? Let's bring our kappa and let's try and relate that to our capacitance C. So can we tie this into what capacitance C is? So let's start with the definition of potential. The new potential between the plates after we have the dielectric stuck in there is the new electric field E times the plate separation D. So the plates are separated by some small distance D. This new electric field is the old field divided by kappa. This old field times the plate separation, that's the original potential difference. So this gives us a relationship between the potentials and kappa. Delta V of the new plate, or the plates with the capacitor stuck in there, is the original potential divided by kappa. And this matches the experimental result, which I said was observed. When we put a dielectric between the plates, our potential between the plates drops. Okay, so that matches our experimentally observed result. Now we said we were going to try and tie it to the capacitance C. So let's remember that C is equal to the charge on the plates, which is just the original charge, because remember we disconnected our battery and the charge can't move around, divided by the potential between the plates. Let's fill in that our delta VC is delta V naught over kappa. Now my kappa is in the denominator of the denominator, so it comes to the numerator. This Q naught over delta V naught, that's the original capacitance C naught. So this tells us that if we stick in a dielectric, the new capacitance is kappa times the original capacitance. So now we have a relationship about capacitance that involves the dielectric, about the potential, and about the electric field. So this dielectric constant gives us the relationships of what happens to the field and the potential when we insert a dielectric between the plates of a capacitor. Okay, now we previously did an example where we had a capacitance of 1 farad, the plates were a millimeter apart, and we said, what is the area of the plates? And the area of the plates was ridiculously big. They were 10.6 kilometers on a side, as I recall. I don't have the slide handy, so I can't pull it out. Let's do the same example, but let's put a dielectric of strontium titanate between the plates. And let's say that we know that the dielectric constant is 300. A dielectric constant doesn't have any units because kappa is a field divided by a field, so the units cancel. And this is just something you would look up in a book. So let's see if we had a capacitance of 1 farad, plate spacing of 1 millimeter, and a dielectric in there, what would be the area of the plates? So we know that the capacitance is equal to kappa times the original capacitance. The capacitance of a plate without a dielectric is epsilon naught times A over the plate separation D. The numbers we know are that the capacitance is 1 farad, kappa is 300, no units. Epsilon naught is the constant that we know, 8.85 times 10 to the minus 12. You can write units as newtons times meters squared over coulombs squared, or you can go farads per meter. And D is the plate separation of 1 millimeter. Put that in meters. So let's take this expression and let's solve for the area. So area is D times the capacitance divided by kappa times epsilon naught. So I'll put in 1 millimeter here, 1 farad here, 300 here, and 8.85 times 10 to the minus 12 here. I get 3.77 times 10 to the 5 meters squared. This would give us plates that would be, say, 614 meters by 614 meters. I would say that this is still too big. You can't possibly have a circuit with a 600 by 600 capacitor in there. Let's see. So something you might like to think about is how would we fix this? One thing you could do is you could make the plate separation smaller. And to do that, you could separate your plates by a very thin dielectric and then just kind of roll them up tight. Anyway, these are practical things that you would think about if you were ever in the business of building a capacitor.